we'll be teaching you guys partial derivatives today. So recall, the definition of a derivative would be the limit as h goes to 0 of f of x plus h minus f of x over h. For partial derivatives, it's really no difference. And for partial derivatives, you would do the same but with respect to either x or y, since there's two variables you work with instead of one. So if you do respect to x, you would have the partial derivative of x, where the limit of delta x goes to 0 for f of x plus delta xy minus f of xy over delta x. And the same would be for y. Probably sound weird. So if you're taking the partial derivative of either with respect to x or y, it requires a process. For this process requires us to find the derivative regarding one of the either x or y as a variable and the other constant. For example, let's say you're finding the partial derivative of x. In this case, you would find the derivative with x being with regard to x, and then regarding y as a constant, and vice versa for if you're finding the partial derivative of y. Yeah. Cool. So before we go any further, we're gonna need to know the partial derivatives in symbols, or otherwise its meaning in symbols. So generally we use this squiggly d as the partial. It's similar to the d y over dx we've been using all year, except it's slightly slanted. First, I had to point out that in we're going to be using z for f of xy, or could be using that. If we find we're going to x, it will be either, these are all equal to each other. Although the common ones used would be this one and this one.
Okay, so we're gonna do examples now. This is sine of 3x squared plus y, close parentheses, plus 9y squared. So first what you want to do is find partial derivatives in terms of x. First you get, so it's partial f over partial x is equal to the derivative of the outside, which would be cosine of 3x squared plus y, and then the derivative of the inside, which would be 6x plus 0, because y is a constant, and then that's in parentheses, plus 9y squared. That becomes a 0 because, again, that's a constant. So then you just get this. Then you want to find it in terms of y, so you want to do partial of f over partial of y is equal to the inside, or the outside, of course, cosine 3x squared plus y, and then you take the derivative of the inside. X being a constant becomes 0 plus y, which becomes 1, and then you want to add the root of 9y squared, which becomes 18y, and this is how you do it.
So we can also plug in points or values in when finding partial derivative. Let's say you have point A and B, where A would be the point for x and B would be the point for y. If you find the partial derivative with respect to x on point A, B, you would find the partial derivative. You get the partial derivative x and then plug in point A, B. You would do the same for y as well. Another thing I'd like to mention is that there can also be more than 3 variables when taking partial derivatives. When you do this, you would add more variables like z, assuming you're not using z in place of f of x, y, etc. If we're finding, let's say, with 3 variables, let's say, it would be f of x, y, and z. The derivatives will be f of x, then x, y, and z, and then the rest will be the same regarding the variables you're taking the partial for.
Okay, so let's start with an example. Given this equation, let's see what the partial derivative would be given this point. If you wanted to find the partial derivative for x, you would start with x. After finding the partial derivative, you would plug in the points. 2 doesn't get plugged in because, and then you end up with 2. So now let's try to find the partial derivative for y. So plugging in the point 1 and 2 would give you -1 because there are no variables, and this is the partial derivative for 1, or for y. Okay, so let's now do the example for if you have 3 variables. So you want to first start, if you want to find the partial derivative for x, you start there first. Then you just solve, remembering that chain rule. Then remembering that the x and z are constants in this case, you only take the derivative of 3x, ending up with that. And then again, z is a constant, so this becomes 0. Next, you want to find, if you want to find it for y, then you just remembering chain rule. And then again, the constants. So you only take the derivative of this because constant again. Now in terms of z, again, chain rule. And then the constants again. This time though, when because z is the variable, you just take the derivative, which ends up being e to the z. And that's that.
Before we end this lesson, we have to talk about higher order partial derivatives, and a higher order partial derivative is the second order or above. But for the sake of this lesson, we're only going to be focusing on the second order. So here we have the symbol that we're using for the second order, which is the second derivative of the function in terms of x. So for this, you're going to have to first take the partial derivative of that, and then what you get from there, you're going to take the partial derivative again, which will give you f of xx. And if you want to do it for y, it's the same as that, however, it will be in terms of y. Next, we have the mixed second order, which, as you can see, it's similar to the up here. However, it is the second derivative of the function in terms of y first, then x. So for this, you're going to take the partial derivative of y, and then what you get there, you're going to take the partial derivative in terms of x, which will give you fy of x. And if you want, or you can also do it in terms of x first, which is the same, you'll just flip it. There are some cases though where the second derivative is symmetrical, so no matter if you flip it or not, you'll yield the same result, but that is only in some cases. And again, you can have more than 3 variables, but it is the same process as this. You'll just have how many other variables of the order. So now we're going to solve an example of a mixed second order partial derivative at point 1, 2. So first we're going to solve with respect to y and then respect to x. Since we're solving with respect to y, x is treated as a constant, so this will be 0. 2x squared plus 6xy plus 4x plus 15y squared. And then now with respect to x, so 4x plus 6y plus 4 plus 0, because y is treated as a constant in this case. So now that we've done that, we have to plug in the points of 1 and 2. Which adds up to 20. Partial derivatives can be applied to many different parts of our lives. One thing it can be applied to is physics. In physics, it is in fluid dynamics, electrodynamics, turbulence, and in many other aspects of physics. It can also be used in areas that you wouldn't think, like photo processing. In photo processing, partial derivatives are used to better edge detection when you're resizing an image. It's also used in economics, because in economics there are many different variables when you're solving for supply and demand and the rate of change for said variables. And also it is used in contour graphs. In contour graphs, partial derivatives allow you to solve for the gradient, which can be represented by a change in color. And with that change of color, you can create topographical maps, which show the change in altitude